Thank you. Good morning, everybody. Welcome to the last of how many lectures? I dare not count. I'm amazed at your resilience. 113. Okay. Right. So we were talking about active model H. And we got to the point where we were thinking about the stress tensor generated by the phi field and the active part of this, which came out as some kind of activity parameter whose sign depends on extensile versus contractile, grad phi, grad phi. And I did mention that there's a term exactly like this with a k, grad phi, term in the free energy part of this. The point being then that what this does is it effectively adds or subtracts from the square gradient term as far as the mechanical stresses are concerned. But it's important, something I didn't say last time, is that this is this term here, and so the shift in what is effectively a shift in the interfacial tension is only in the Navier-Stokes equation. It's not in the diffusion equation. So effectively shifts interfacial tension in the Navier-Stokes equation. So it's like I have fluid of a reduced or even negative interfacial tension in Navier-Stokes, but it has no effect in the diffusive sector. For which the tension is always positive. Sorry? Okay. So, and I drew a diagram. So what that means then is that the diffusive flux, or diffusive current, which I wrote down, this is always acting to maintain stable interfaces. In other words, to, well, maintain stable interfaces and reduce the total interfacial area. So the diffusion equation doesn't see this term, and the diffusion equation is trying to coarsen the structure through exactly the same mechanism as in ordinary model B. So this leads to coarsening L of t, which goes like t to the 1/3, but that's not the point at the moment. It doesn't actually do that. So let's take the contractile case. So there's actually minus sign in this as well. So the contractile case, so let me just draw this cartoon again. Here's a particle on the interface. Its direction of propulsion, because it's p, its polarization vector, is aligned with grad phi or minus grad phi. It makes no difference to this diagram, because what we have here is a fluid flow around this particle with the arrows like this. So you see that that is like a negative surface tension. It's trying to make the interface stretch. So the propulsive flow stretches the interface spontaneously. And if zeta is large in magnitude and contractile, so this is zeta negative, the tension in the mechanical sector, so in the Navier-Stokes sector, is itself less than 0. So this obviously is opposed by the any interfacial tension coming from the free energy part, but if there isn't any from there for the reasons I said before, or if the contractile parameter is big enough, then I have a negative tension in Navier-Stokes. So what I have then is, at small scales, I've got a competition now between these two processes. One is the mechanical stretching of the interface because of the fluid flow. At small scales, though, and it's easy to check this, the diffusion is always going to win over the Navier-Stokes part. So small scales, diffusion, which involves the diffusive current, wins. But at large scales, essentially this hydrodynamic effect wins. The same is true, by the way, in passive model H. If I look on the scale of an interface, everything is diffusive. If I zoom back out and ask what controls the coarsening at the largest scales, it's the fluid flow. So this means that the system can, in principle, and in fact does, so it finds a balance point at some finite L, L here being the structural scale of the pattern. So at this point, coarsening is balanced by active stretching. So if you do look at this system numerically, you get the following thing. So L of t is the domain size. So I said wrongly, this was t to the thirds earlier. You have a diffusive regime, and then in passive model B, or the extensile active case, this ends up with a linear slope, so t to the 1, extensile or passive. But if it's sufficiently contractile, you do find instead that this asymptotes to a constant scale, so sufficiently contractile. So this is in a paper by Tirabocci et al., if I can write that. So this is microphase separation. Microphase separation replaces bulk phase separation in the very contractile case. So via contractile hydrodynamics. So this is interesting for various reasons. Something I said previously, and which may have come up in earlier lectures as well, is that in experimental self-propelled colloids you do often see arrested phase separation, in the sense that you see formation of dense clusters which reach a certain size and then stop growing. So you can think of this as a possible candidate, and possible is definitely underlined here. For cluster phases. And the only problem with that is that almost all of the experiments on self-propelled colloids actually have the self-propelled particles swing around near the bottom of the container. In other words, they actually swing around very close to a wall. And because they're swinging around very close to a wall, it's not actually true that a momentum-conserving model is the appropriate thing. In other words, the problem with this explanation for cluster phases, firstly, they would only happen in contractile swimmers, and we don't know whether that's true or not. But the problem then is that the experimental cluster phases, so cluster phases are quasi-dry. So this may be an important factor in the behavior of bulk self-propelled systems in a solvent, but it doesn't really go very far towards explaining the experiments that we do have of self-propelled particles near a wall, which show cluster phases, but for which active model H is not going to be the right model. Yes, Julien? Well, because it's hydrodynamic, actually. So I misstated earlier that was 1/3. It's 1/3 in model B. In model H, it's 1. Austin. Yes, if you okay, so here, Chaikin science. So first author is actually Paolucci, which I can't spell, so I'll put Chaikin. That's about 5 years ago. Also, is it Thurkauf? That's a PRL again, 3 or 4 or 5 years ago, a bit less maybe. Thank you, Julian. Yeah, good. So okay, so that's interesting, but it doesn't really explain that, the cluster phase stuff. So what I mentioned before is that when we derived active model B, so that's the dry version of this model, the microscopic coarse graining gave us various, well, it gave us specifically one very interesting term, which is the lambda term. But what I'm going to do now is generalize that and try to be more systematic, so actually more top down. In other words, what active terms are possible? And we've only found one of them, but there are others, or at least one other which matters. So that leads us to look at this. So this is rather inelegantly called active model B+. And I'm going to write it down and then talk about it. So the usual structure, phi dot is minus div j. I'm going to write, and I'm slightly changing the notation over here, I'm afraid, jd. So this d now stands for deterministic. Because I want to talk a lot about the form of the deterministic current. There's also the usual square root of 2d unit white vector. So that's what j is in this equation. And now the question is, what is the form of jd? So far, we have, if I set the mobility to 1, as I did in active model B, I have a term which is the gradient of an equilibrium chemical potential, so an equilibrium-like term, grad df d phi. And then I had the lambda term living in the chemical potential, so I can write this as minus grad lambda grad phi squared. So this was active model B, and here is the plus. So f, as usual, over 2 phi squared, b over 4 phi 4, k over 2 grad phi squared. So this is the new term. And using John Toner's principle, this is of the same order as that. In other words, I look at the J equation, I've got 2 phis and 3 grads, and here I've got a different combination of 2 phis and 3 grads. So, if it's not forbidden, it should be there. That's what John Toner said, and I agree with him. But it's interesting that this didn't come out of the coarse graining we had. It does come out if you coarse grain a slightly more complicated model, so it's always good when you see a term which you think, you know, is allowed. It's quite, you do feel better if you can find a microscopic model that does give it to you, and we have done that, but it's not really interesting enough to present that calculation as well as the other one that I already showed you. Okay, so the key thing about this then is that the curl of the deterministic current is not equal 0 anymore. So although the term lambda was well motivated by the microscopics, it unconsciously, if you like, created a big restriction to the form of the active current, for which there's no reason to believe that's true in general. Okay. So that's a structural change to the model. It's not a detail. It's something which changes the basic form of how the active current behaves. Yes? Well, I can. The reference will come up. Well, actually, I may as well put it up here now. For microscopics. But also for everything else I'm going to say in this lecture, actually. So, and everything else. Chung et al. Archive. So this is on the archive now, 1801. 0.07687, but you can obviously look for that name. It's a relatively unusual one. Yeah, and this is coming out in PRX shortly. Okay, so the thing, though, which is interesting, is that in one dimension, this isn't an independent combination of grads and phis from that. And this is, again, something which came up in John's lecture as well. So if I put indices on all of these, then they are different in general. But in one dimension, they're not. I can just change one into another. So that has an interesting and deep consequence. So, which I will first write and then first put the consequence and then write what I've just said about that. So if I look at phase equilibria at the mean field level, which means doing what I did last time, constructing a one-dimensional density profile and finding the densities which can coexist and also finding the spinodal and so on, then the point about that is that's a quasi 1D geometry. Then I get same as A and B without the plus, with an effective value of lambda, which is lambda minus zeta over 2. So at mean field level, I get exactly what I had before for the phase coexistence conditions, but with a shift in lambda given by this. And the reason is that in 1D, where there's no curl anyway, the curl is not defined in 1D, so in 1D only, it is true that lambda grad phi squared is equal to 2 lambda del squared phi grad phi. But you can check for yourself that that is not true in 2 dimensions or above. Okay, so what that means is at the mean field level I can just draw the phase diagram that I had before, which I'll just briefly indicate again. What I had before. So this is now lambda f. I have some spinodals down here. That's phi. I won't put in all the labels this time, but if you remember, what happened was the binodals did that. So they approach the spinodal at large activity parameter, either positive or negative on the left or the right-hand side. Okay, so let me draw this slightly better. So mean field theory says shifted binodals and bulk phase separation inside these. So that might be disappointing, because it looks like this extra term here isn't going to change the phase diagram, and in particular it's not going to give us anything like microphase separation or cluster phases. But in fact it does. So let me say more about that, and that will occupy quite a bit of the rest of the lecture. So let me just shade in a region down here. And say what really happens. So if you do, it's easy enough to do, well, it's not that easy actually, but you certainly can do simulations of this model numerically. And you do that with finite noise, of course, otherwise you would end up pretty much with the results I've said. So simulations with full noise, well, noise anyway. So non-zero D. So I now have 2 parameters. I have my parameters are lambda and zeta, and as I've said, at mean field level, this is the same as lambda minus zeta over 2, comma 0, right? So equals lambda minus zeta over 2, comma 0 at MFT. But in general, these are different parameters. And what you find is that if you actually well, obviously we know what happens when zeta is 0. That's the standard model. So clearly, that's active model B. And I would have told you already if that wasn't giving qualitatively right answers in this mean field theory. So the mean field theory is confirmed for lambda zeta equals lambda 0. In other words, when there isn't the curly term here. But microphase separation is instead seen and it's seen in a certain region of this parameter space here, but the region includes when there's no lambda term, but there's only the zeta term. So when there's only the zeta term, I can still map it onto an effective lambda for the purposes of mean field theory, so I don't, at that level, have any reason to expect anything different between this and that, so long as I change, as I choose a value of negative lambda over 2 to stick in this position. But no, that's not right. So in the shaded region over here, what I get is positive zeta, something I'm going to call the bubble phase, and for negative zeta, a cluster phase. Or at least the closest you can get to a cluster phase with a scalar field. So say we take this case here, positive zeta, and I'm just going to draw some diagrams, -1, +1 for phi. So as I take a line across here, I would expect in the mean field a region of phase separation here. And have I got this the right way around? Well, yeah. Which is the shaded region? That is the shaded region. Zeta. Let me just check I'm going to get this correct. Yeah. So when I'm going to have a vapor here, and the question is, do I get ordinary bulk phase separation when I enter this region? And the answer is no. What I see is vapor. Then as I come into the left binodal, I see vapor liquid, except that the liquid, so this is vapor and this is a bubbly liquid. In other words, in this liquid, I have voids of vapor as part of the steady state structure. And then if I go into the shaded region here, I have a uniform bubble phase, so but I still have voids. So this is now liquid with holes in it. And then eventually I do emerge on the right-hand side of the shaded region into a normal liquid. L. So shaded region. And something that is maybe not immediately apparent, but this entire model, if I change phi into minus phi and lambda and zeta into negative lambda, negative zeta, I just can flip the whole thing over. So I just interchange vapor and liquid here. So that would then be a cluster phase because it would be liquid droplets in a sea of vapor, right? So yeah. Let me just write this for zeta less than 0 case. Yeah. Who was asking? Yes. Sorry? No, there are two. You obviously, to see this, you need two, and also in one dimension I couldn't. In one dimension, these things really are the same. So there's no way that I could get a difference even beyond mean field theory. Whereas the reason that this makes them, the mean field theory looks the same is because mean field theory for phase coexistence is a one-dimensional theory of a 2- or 3-dimensional system, because it just assumes that I've got a single coordinate normal to the interface along which the density is smoothly varying. Yes, Julian. The theory that gives me what? I don't have a theory. Well, I mean, at the moment, I'm just telling you what happens in a numerical simulation. Well, that may be one way of saying that is to point out that the size of these bubbles depends on D, and actually seems to, if I turn off D, it gets bigger and bigger, so that I end up with an ordinary phase coexistence instead. So that's something I should maybe I think I will come back to that. Okay. In fact, maybe I should just write that down now. Equilibrium bubble size depends on D, and not in a way that we understand, by the way, but just numerically it does. So that's another argument as to why MFT is not sufficient to fully explain this. What we will find is if we look at the kinetics with the mean field theory, then you can at least understand roughly why this is happening. Okay, so let me make some comments. Role of zeta term. Firstly, microphase separation, clusters and bubbles. Secondly, as previously advised, curl of JD, so that in a deterministic steady state I don't have to have a vanishing curl, so I can have real space currents, but in fact for the purposes of this, what's going on here, you don't see very much of that. So they will be important in some other geometries for sure, but the thing which is more striking when you do these simulations is that you see phase space currents which are much more visible. So phase space currents are pronounced. And in case you're still sort of not quite sure what I mean by a phase space current, in fact, what you see in these simulations is a very graphic example of that. So let me just draw this. Suppose I look close to the interface here between vapor and the bubbly liquid. So this is now a little patch near the interface. So suppose there happen to be no bubbles in that region. Then what you observe is that through the noise term, you can get nucleation of a bubble. So here's this. And then you see growth of the bubble. And then you see something interesting, which is that the bubble pops out into the vapor and disappears. So this is a circulating current, in the most general sense of the word, in configuration space. At no point in this process can I say there's a J which is going round and round in circles in real space, but in the bigger space of configurations, that is a circulation, and that is prohibited by the principle of detailed balance for equilibrium systems, because if I run that movie backwards, I see something totally different. I see a strange engulfment of a bit of vapor at the interface turning into a big bubble which then shrinks to zero. And if you look at these movies, that's something that you basically don't see in the active model. Okay, so I'll put that reference back up. Archive. Right. So how do we understand this? Well, we have an explanation of this, which involves looking at the dynamics of coarsening. Yes, Austin. Well, it does look like that, doesn't it? Except, of course, that is a steady state, whereas boiling, the vapor phase is growing in volume and the liquid is disappearing. So you'd have to have a, you'd have to, if you had a boiling system with a cooling at the top, So you'd have a heater at the bottom, cooling at the top, so that somehow the volumes of the two phases stayed the same. Then yes, you could think of it like that. So it is interesting. One of the interesting questions which this whole area presents actually is, when do you see things in active systems that you could also see in a driven system, so something where you're basically driving the system at the boundaries, say you put a heater at the top and the bottom, and when there's something which is uniquely active. But we don't have an answer to that question yet at all. Yes. When? Well, you mean because you see the cold stuff coming down the sides or something? Yeah, you're probably right. So I haven't thought about that in detail, but yes. So anyway, you'd need something to maintain steady state to even make it look like that. Yeah. Okay. So we're going to think more about this process, because the way phase separation happens in passive systems is that, at least in the non-spinodal region, and even in the late stages in the spinodal regime, you get droplets, and the droplets grow. And some droplets grow, some shrink, and that's the kinetic pathway between a uniform phase and the bulk phase separated state. So what I want to do in my final hour is first explain how that happens in the passive case. So this is a kind of throwback to the first couple of lectures where I was talking mostly about passive stuff. And then if I have time, say what changes in active model B+. So let's look at coarsening dynamics. So are there any questions on what's here? Yeah. How? Well, that's a good question. In practice, it seems to be noise. In other words, this basically diffuses to there, at least in the simulations we have, which are noisy. Probably there would be a deterministic motion of that towards the surface if the noise was not already dominant, I think. But, I mean, as usual in phase-separated systems, there's a kind of exponentially small interaction between surfaces. We haven't tried that. So yeah, Austin again. A plus. Not yet. Probably we should. I'm not sure what it would describe at the moment, because you have to be non-conserved. So it won't be active particles, but it'll be something active and non-conserved. Active non-conserved scalar. Yeah, well, it's worth thinking about what that might be. Okay, so let me go back to the passive case first then. So coarsening dynamics. Passive model B. So this will lead to something called the Austral process, which many of you will know, and some of you will know of, but not have seen the explicit construction of it for the simplest possible model, which is passive B. So what we start with is a non-kinetic problem, which is, consider a droplet in equilibrium with a finite volume of vapor environment made of vapor. So the picture is this. I have a finite system, and I put a droplet. So this is going to be phase 2. So phi equals phi 2, phi equals phi 1. So phi 1 is the vapor, phi 2 is the liquid. It has a radius r. So I'll remind you of this. This is the equilibrium free energy. Well, minus phi b plus phi b would be the two minima here. And the first and important statement is that this system, which is in static equilibrium, has not quite got phi 1 equals minus phi b and phi 2 equals minus phi b. These are shifted, and they're shifted, as we'll see, because there's a mechanical balance across this interface, which means the pressure inside is slightly bigger than outside. And that's the Laplace pressure due to having a curved interface here. So let's see how that looks like. Flat interfaces first. So I'm thinking now the bulk chemical potential in these two phases. I'm still going to call them bulks, although they are going to be finite in a minute. df d phi and P is mu phi minus f, excuse me, and mu1 equals mu2, and P1 equals P2. So rather as happened in active model B, actually, this second relation, P1 equals P2, is going to change because the pressures are going to be different with the curved interface. So phi 1, 2 equals plus or minus phi b, but there are going to be now corrections in 1 over r. So this is only true, the canonical construction, the common tangent is only true in the case of an infinite radius of the droplet, or equivalently a flat interface between the phases. So what happens for a finite droplet? So Laplace pressure, so this is force balance across the curved interface of the droplet. So I'm going to draw half a droplet, P2, P1, and if I resolve the pressure force across the interface, I get an upwards force, which once it's been resolved is the pressure difference times the area of this disk. P2 minus P1 pi r squared. So this arrow means upward force. But if I think of this hemisphere here, there's now also a downward force because there's an interfacial tension between the top half of this droplet and the bottom half. So the downward force is 2 pi r times sigma. Sigma is the interfacial tension. So P2 is not P1, it's P1 plus sigma over r, and in d dimensions d minus 1. So you need curvature. So this is another thing which vanishes in 1D. You can't have curvature of the interface in one dimension, but that's the general result in higher dimensions. So how do I maintain static equilibrium in this case of a finite droplet talking to its own vapor? So I still have to have no current. So J equals 0. That means that grad mu equals 0. So mu1 equals mu2 still. So this is in a diffusive system, this is the last result ever to go. And we kept that result in active model B plus, and it's always true in active model B, sorry, and it's always true in this passive case. But what changes is the pressures. Okay, so then what's the effect of that? If I go back to the free energy curve, again, apologies to those of you who are already intimately familiar with this. What happens is this. Oops. One day, when I've retired, I'll learn how to use chalk without breaking it. So the pressures are not the same. That says that the intercepts are not the same, right? They have the same slope. If I draw tangents to this, but there'll be a pressure difference. So what that means is that there's actually an offset. So minus phi b plus delta is the point of tangency here, and plus phi b plus delta is the point of tangency there. These minima are parabolic, so long as the radius is large, so this is a small shift. The shift is the same in these two wells. It's only at beyond quadratic order that I'll notice that this is going up here, and that's flipping over. So mu1, mu2, I've got, as I've said there, phi 1 equals minus phi b plus delta, phi 2 equals plus phi b plus delta. So if I look at what the chemical potentials are, mu1 equals mu2, and I can write that as the curvature of the free energy at plus or minus phi b times delta. Again, expanding everything to leading order in small deviations here, so this is all large R limit, but not infinite R. And then if I look at the pressures, P1 minus P2, well, that's given by the difference of these two intercepts. Of course, I've horribly exaggerated this, but it's easy enough to check for yourself what that is. It's minus twice the same curvature at phi b times phi b times delta. So you expect this shift to be of order delta, and it's just given that this is a quartic potential, you can easily calculate what it has to be given the inequality of the pressures according to this. So I have a relation now. This tells me what delta is given sigma and R. So 1 over 2 f double prime at phi b d minus 1 sigma over R. And obviously this is a redundant statement, but this is also in problem 7 if you really want to check it after you've got home. So okay, so this is what happens for a droplet, one droplet in relation to its vapor. So that's actually Okay, just about to resume. Okay, so this is a calculation for how a droplet can coexist locally with its vapor. That's basically what this calculation is about. And now we can extend this to the multi-droplet case and apply this argument in the neighborhood of each droplet. And what we'll find then is that because the droplets have different sizes, there will locally be different values of delta, and so there will be different local equilibria, and that will drive material to flow from, as it happens, small droplets to large. So let's look at this next. Many droplets. So here we have one of them. This radius is r. Let's draw a radial coordinate out there. So just outside in the vapor, minus phi b plus delta, which depends on r. And just inside, plus phi b plus delta of r. So those are the local local densities which can coexist across a curved interface. So as r goes to infinity, what do I have? Well, the idea in the way this is usually treated is that this will go from whatever the local value is here for this particular droplet to some kind of ambient so-called supersaturation, which I'm going to write as epsilon. So phi equals minus phi b plus epsilon. So epsilon is the supersaturation, which is something to do with delta for the average droplet size at any particular time. In other words, this particular droplet at large distances just sees a bath of other droplets. If you calculate their average size, that gives you an estimate of the displacement from the bonodal density of the composition out there. So r bar is the typical droplet size. It is possible to do this significantly more formally, by the way, but I won't. So what we have then is phi r. I'm going to write this as minus phi b plus an increment phi tilde, which is a function of r, and phi tilde at the surface of the droplet, so radius r plus, so just outside the droplet has to be delta, because that's the equilibrium condition across the curved surface, and far away this is epsilon. Okay, so I'm thinking about as a mean field-like description of what will now be the dynamics of this droplet, namely it has some local supersaturation that doesn't match the ambient far field one, so that means there will be a flow of material either onto or off of the droplet, depending actually on whether r is bigger or smaller than r bar. So let's write some equations of motion. So I'm going to say that the phi tilde, so this correction, is everywhere small, so this whole thing assumes that all of the radii are sufficiently big. So small phi tilde, which is the same as large r and r bar. Phi dot, which is the same as phi tilde dot, is minus div j. J equals minus grad mu. And mu is a function of phi, and therefore depends on phi tilde. And mu is linear in phi tilde because I'm only slightly displaced. So phi tilde is the distance from this point, say, out here. So this is quadratic, so mu is linear. So I can write this as minus alpha grad phi tilde, and there's an order del cubed here, which I'm not going to worry about. And alpha is the curvature again at the binodal. So now we make a quasi-static approximation. So the idea is that these droplets are very slowly exchanging material with this kind of distant bath, and therefore with each other. So quasi-static, which is phi dot equals naught. So that means that div of that, so del squared phi tilde equals 0. So I have to solve a Laplace equation for the excess density here with these two boundary conditions. And that's something which you can do and could have done, hopefully, at least after your first year at university. So solution with these boundary conditions is phi tilde is the far field epsilon plus the difference between delta and epsilon times something which is equal to unity at the surface of the droplet but decays like 1 over r. So that's just Laplace's equation with spherical boundary conditions, different value at the edge of the inner sphere and at infinity. So I just subtract that off and I have a 1 over r field for the difference here. So that's the steady state solution of effectively the diffusion equation within passive model B. So having got that solution, I'm now in a position to calculate the gradient of phi tilde, so the gradient of phi, at the surface here, and that will tell me the flux. That will tell me whether material is coming onto the droplet or leaving it. So J is now a function of r only, and it's along the radial direction. So radial flux J at, and I'm interested in the value at the droplet surface, J of r plus, and given the equation for J as grad of phi, this is phi, so I have minus alpha d phi tilde by dr at the droplet surface, and that is alpha delta minus epsilon r over r squared at the droplet surface. So there's a 1 over r there. So there's no flux if the droplet happens to match the ambient supersaturation, but otherwise there's a flux onto or off of it, depending on whether it's bigger or smaller than r bar, because that determines the difference between delta and epsilon. So now we can relate that to the rate of change of droplet size. Here, this is the curved surface. I've got phi b plus delta on the inside. That's the radius. Minus phi b plus delta on the outside. So these are the concentrations or the phi field values directly either side of the interface. And let's write J, the radial flux, in that direction. Here there's a concentration jump, and that's what this was defined as. So the concentration jump across here, across this interface, they're both shifted by the same amount. So it's still, as in bulk phases, it's twice phi b. So in this model, it's just the difference in phi between the left and the right minimum. They both shifted a bit, but that's still 2 phi b. So that means that I can calculate, because there's a current here and the concentration jump, if I know the concentration jump and I know the flux, then I can calculate the rate of change of r. It's the speed at which this interface is progressing as a result of stuff arriving or leaving from the outside. So mass conservation. 2 times the phi binodal. So the concentration jump, which is a positive number, times RB, R dot, is negative J. In other words, if the interface is moving outwards, this is the dense liquid, that's the vapor, then I have to have a current which is inwards, otherwise R dot is decreasing. So let's put those pieces together then. I know the flux, I know the relation between the flux and the rate of change of R, so that tells me a closed equation for R dot as a function of R, and here it is. Well, it's not quite closed because it involves R bar. R dot equals 1 over 2 phi b alpha, which is the second derivative, over R times epsilon minus delta, which depends on R. And epsilon depends on R bar, the kind of global average of all the droplets in the system. And yes? Yeah. Yes, so the point is that this interface is narrow. There's a slow quasi-static diffusion, so at all times the equilibrium between just inside and just outside has to be as if it was fully equilibrated. And it's only the fact that this value here is different from somebody else's that gives you any deviation from equilibrium. Yeah, so there's a local equilibrium assumption there. Yeah, I mean, technically you could. Okay, so I'm working to expanding in one of R basically. You could imagine some physics that was going to alter this at small radii, but from other information about the passive case, we know it's not. There isn't anything like that in Model B. Okay. Ah, yeah. So you could, yes, you could imagine that, but yes, instead we'll see something which is more dramatic. So, and this delta is sigma over alpha R phi B, which is up there somewhere before I erased it. Okay, so what have we got? So we have this interesting structure, which, as I say, will be familiar to any of you who know about Austral ripening. We have R dot as a function of R, which has an unstable fixed point here, R star of epsilon, and does this. That is what this equation says. 1 over R, decaying like 1 over R squared at large radii with a positive value and negative for R less than basically the R set by epsilon. So R star and R bar are technically slightly different, but not quite. Okay. So the point about this, large droplets grow. Small ones shrink. I have a colleague who was giving this kind of lecture to some high school students, obviously without the equations and not about active matter, and they thought this was terribly unfair. So, this is called the Austral process. So, if we think what R star is doing, this is the kind of, this point is moving because epsilon is changing. The reason epsilon is changing is because the droplets are getting bigger, because the big ones are getting bigger and the small ones are disappearing. So epsilon, which depends on the mean droplet size, is floating slowly to the right as a function of time. So R star is a function of time, and I can think of that as, a function of epsilon, which depends on time, and it's basically the typical droplet size. Related to R bar by some order unity factor. So I can look at the equation of motion for this, and this is now deliberately very hand-waving. This looks like 1 over 2 phi b alpha over R star, delta of R star. So I can't say that R star is exactly R bar, because then this point would self-consistently stay where it is. That's not what happens. The droplets are getting bigger, so the average droplet size gets bigger. This looks like alpha over phi b sigma over R star squared. So that says that the typical droplet size goes like t to the 1/3. And from that you can calculate the typical supersaturation, which is delta of R star goes like t to the -1/3. Okay, so this whole theory, of which there's a fully quantitative version which actually looks at the population size distribution of droplets and so on, is Lifshitz-Sliozov, also called Lifshitz-Sliozov, or Lifshitz-Sliozov-Wagner, although those were two independent things, 1958. Although Austral understood the basic physics of what's going on long before that. Okay, so that was a big detour back into the realm of equilibrium dynamics. And now I want to just spend the last little bit at least saying what changes to this picture in active model B+. In other words, what is it about the coarsening of droplets that somehow in the active case can escape this? Yes. Yeah. Have I dropped that somewhere? Let me just look at my notes. Yeah. That and I think that one was the typo, wasn't it? I think. Because I have there's a phi b in P1 minus P2. Yeah, so I had, just going back to where we did have this one, or whichever way around it was, minus 2 f prime prime phi b delta, and then I wrote, I think, because I'm just copying my notes now, 1 over 2 f prime prime d minus 1 sigma over r. That's what you're referring to, right? And there should be a phi b here. Just solving that equation, right? Okay, let me correct this. Your attentiveness in lecture number 135 or whatever is impressive. Right, good. Okay, so what changes? So I have 25 minutes left. I don't want to spray too much detail all over the blackboard, but there is quite an interesting structure to this, so at least I hope to show you what the structure is that allows this otherwise rather general kind of theory to be circumvented. Okay. What changes in AMB plus? And the plus will be needed. So here's J. Now, I'm only going to talk about the deterministic part here. This whole thing, there was no noise here. There's a diffusion equation, but there's no noise. The Lifshitz-Shazov process, if I start with the distribution of droplets, it is essentially a deterministic evolution which drives the system to big droplets away from small ones. So I'm not going to worry about the noise. So let's say that. Drop the noise for now. And let's write this in this form. So mu e, so this is the free energy part. So minus a phi, b phi cubed, minus k grad phi squared. There's a mu lambda, so the lambda term does live inside the chemical potential, so this is where it sits in the equation. So mu lambda is lambda grad phi squared. And then I have the zeta term, which is del squared phi grad phi. And this I'm going to call J sub zeta. And there could be noise if I wanted it. So what is J sub zeta? Well, I've written it down, but I can just remember that I'm going to take the div of this J. So in fact, and this is possibly a bit confusing because I mentioned the importance of this term being able to give you a curl. But if I look at the time evolution of the density, a current which is a pure curl doesn't actually change the density. It's important if I'm looking at patterns of circulating bacteria and so on that there's a rotating current. But a pure rotation, pure circulation, leaves the density unchanged. That's because div of a curl is 0. So I can always write this as the gradient of something, where I project out this into a gradient part, so put a mu zeta on here, plus the curl of something else. For want of a better symbol, call that A. So this is actually just the Helmholtz decomposition of J. So any vector field can be turned into a gradient part and a curl part, and this is irrelevant to phi dot. So when I say that, okay, well then it looks like I'm sort of contradicting myself here, because I'm then going to have J is the gradient of something. Well, what I'm saying is, as far as phi dot is concerned, I can define a thing, which is the sum of these three terms, whose gradient is J, up to a curl, and therefore that's all I need for the phi dynamics itself. Okay, so I can because we know how to do Helmholtz decomposition of a vector field, we can construct this mu here, and we'll immediately see something rather important about it. So as a function of r, I'm just going to write it down. Well, in my previous notation, this rather informal one, it's the inverse Laplacian on the divergence of Js, which is another way of saying in 3 dimensions. So that's, if you like, a notation which would apply in any dimension, but in 3 dimensions this should look rather familiar. dr prime 1 over 4 pi mod r minus r prime div, j zeta at r prime, and this is mu of r. So in 3D. So what I have then, if I want to do this Helmholtz decomposition of a vector field to turn it into a gradient part and a curl part, then to get the gradient part, I take the div of it, and then I do a Coulomb integral. And this is something that you may start ringing a few bells from electrostatics here. So in electrostatics, if I know the electric field, and it's not got a curl because there's no dB by dt, then I can take the divergence of the field, and that gives me the charge density, and that's the Coulomb integral for the charge density. So the divergence of this looks like a charge density for the purposes of calculating mu. So I have this nice structure, but the key thing about it, of course, is that this is not a local function of phi. It's an integral function of phi involving a Coulomb kernel. So, non-local in phi. So that's enough to make you have a good reason to think that the ordinary Ostwald calculation is going to have to change, because the one thing that was certainly assumed there is that wherever you look you have some kind of local free energy structure from which you can derive the chemical potential. So, and just for completeness, I'll write that down. So this is a Coulomb integral. Can't even write. Coulomb. With minus div j zeta as the charge density. So something involving lots of gradients of phi is like a charge density for the purposes of calculating this bit of the chemical potential, and it's non-local because of the Coulomb integral. Okay. So spherical symmetry. So we're thinking of a droplet now. And let's see how this changes the story. There's a phi 1 in here, and I'm not quite sure what it is anymore, so it's phi 2. This is phi 1 somewhere outside. Okay, so in this geometry, let's just think about what this might look like. So so I'm assuming the whole field around it is symmetric as well, which is in fact what we do in the Ostwald calculation when we just treat the whole of all the other droplets as just a distant bath. That's what makes that calculation simple. So in this geometry, grad phi equals phi prime, meaning d phi by dr. Del squared phi is phi double prime plus d minus 1 over r times phi prime. So that's what the Laplacian looks like in d dimensions with spherical symmetry. So mu at r, so this is a function of the radial coordinate only, is mu e, as usual, plus mu lambda, plus mu zeta. So mu e is a phi plus b phi cubed minus k del squared, so phi double prime plus d minus 1 over r phi prime. This is just lambda phi prime squared, and mu zeta is this thing. Well, mu zeta has a simpler form in this geometry because you know how to solve the Coulomb problem for a sphere. In this geometry, I effectively have a charge density, which is the div of that, so one more grad, that lives on the surface of this sphere. And what I want to know is mu, which is the, no, he did tell me he was leaving early. You'll all start walking out now. So I have a charge density, which is the div of this, so one more gradient, which lives on the surface, and then at that charge density I have to calculate mu, which is the potential from it, right? So if I have a shell of charge, you can all leave if you want to. If I have a shell of charge, one thing you know in spherical geometry about the electrostatic potential is it has a step between the inside and the outside. Just like the, yeah, okay. So, what that means is in this geometry I can do the Coulomb integral explicitly, and I get mu zeta is integral from r to infinity of a coordinate s, so that's the dummy variable zeta del squared phi grad phi. So what that's also saying is saying I can get in a spherical geometry, I can get the potential, which is this mu, is the potential-like quantity in electrostatics, from directly knowing the field, which is this vector that is the thing whose divergence is the charge density. So it's like this is the electric field, its div is the charge density for calculating the chemical potential, but because I've got spherical symmetry, I can just integrate the electric field and I get the chemical potential at the surface from that integral. Okay. So compare V is minus integral of E. Right. That's the electrostatic analog. Okay. So I told you already what the main effect of this is, and that's to give you a step in the zeta part of the chemical potential at the interface. So I don't want to give you every detail. Writing this, there's another line of algebra which I'm not going to write down. Mu zeta is minus zeta over 2 phi prime squared at r plus d minus 1 zeta integral r infinity phi prime at s squared over s ds. So this is a rewrite of that thing, in fact. Okay, so this is all in the Chung et al. Archive paper that I mentioned. Okay, so this is the non-local part, non-local bit, and again, strong analogy with electrostatics. So this is 0 inside the droplet, and it's something, let's call this delta subscript zeta, outside. Now, what I did say was that the last thing ever to disappear in a diffusive system is the relation between the current and the gradient of the chemical potential. And indeed, the chemical potential has to be continuous across this interface. Otherwise, there would be a current. So what that means is if the non-local part, the zeta part, is giving me a jump, then there's also a compensating jump somewhere here, particularly there. So what that does is it gives you across this interface, there's suddenly now a discontinuity in phi, which there never was before. Well, no, there was discontinuity, a different discontinuity in phi from the one that would be predicted in the equilibrium model. So, but mu is continuous. So f prime at phi 1 equals f prime at phi 2 plus delta sub zeta, and therefore mu e bulk, so the bulk part of the equilibrium chemical potential, so the polynomial part over there at phi 1 is suddenly not equal to the bulk chemical potential at phi 2. Right. So the full chemical potential defined that way is continuous, but that means that what I can't do is just say that the two coexisting phases across this curved interface have the same bulk chemical potential, because they don't, because there's a sudden step in the chemical potential coming from the activity which has to be compensated by the bulk chemical potential being different. So you can also think of that as another kind of somehow activity pumping stuff across the interface. It's creating a local mismatch in the non-gradient part of the chemical potential. And the other obvious thing is that only zeta can do this, because the lambda term stays local. I don't have any of this Coulomby stuff going on. Well, yes, but now it's happening to the chemical potential as well. Yes. That's a good way of thinking about it. Yes, exactly. So yeah, so if you think of this in terms of this sort of pumping effect of activity, it's now it's changed the dynamics in a much more fundamental way, because I don't have constancy of mu anymore, or the normal part of mu. Okay. Right. So I'm not going to give every further detail, obviously. So what you can do is construct the coexistence conditions across a curved interface from this. So to construct, so basically what I'm looking for is phi 1 and phi 2, which are dependent on the droplet size. So to do that, I need to do the funny transform. So you can call that the Solon transform, or you might want to call it the pseudo transform into the changed variables, the same as I did before, and with the bearing in mind the shift of lambda. So let's this was r of rho. I'm now going to write it as psi of phi. This is chosen so that k psi double prime equals zeta minus 2 lambda. So this is the equivalent of the thing which we had living in the previous one, and then big phi of little phi of this changed variable psi is defined such that d big phi d psi equals minus f prime of phi. So this is the same as before. I've just explicitly said that I'm now using phi instead of rho, and I just wanted to change the symbol here because r is a bad choice of symbol in the context of this particular calculation, because it's that one. So I don't want to have r sitting here as well. Okay, and so you can calculate a pseudo pressure. So this p tilde is big phi psi minus phi. And so, and you do this. You do a similar step. So you say, well, you find things which are constant, you integrate them across the interface, and you end up with a condition for these. Okay. So again, more details in that archive paper. And what you find then is you can relate the pseudo pressure, which looks like a Laplace pressure, can be written in terms of, if you like, a pseudo Laplace pressure, or a Laplace pressure with a pseudo tension. So I should say that by the time you've done all this, I mean, any intuition you might have had for what's going on is pretty much abolished, even if you're me. So this is really just a mathematical thing. But what, in other words, the pressure when you the pseudo pressure which comes out of this is of the jump in it is of Laplace pressure form. It involves a thing divided by the radius, but the thing is this pseudo tension, and I'm not going to write it out. Equals dot 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 dot. And the point about this, which is crucial, is that this can be negative. So rather, as we had in active model H, where I had a tension-like quantity, in that case caused by the mechanical flow forces around particles in an interface trying to stretch the interface. This is a much more abstract mathematical construction, but in the same way, what it means is the relation between the pressure and the size of the droplet can go into reverse if there's a large zeta contribution. Okay, so I just will say what happens and then stop. So all of this is it's a mean field like calculation, but it's a mean field calculation of the kinetics for droplets. And so it is obviously more powerful than just doing the mean field calculation with a flat interface, which, as I told you, doesn't get you anywhere here. So because we've looked explicitly at droplets, we can see how the kinetics for the equilibrium type of Austral process is changed by activity, and it seems to be changed in this way. So here's the result, and again schematically, and then many more results in the aforementioned paper. Let's plot this as a kind of phase diagram like this. This is lambda. This is zeta over 2. So the first thing I mentioned before is that there's actually the whole model has a symmetry. If I change the sign of lambda and of zeta and of phi, then the model is actually unchanged. So I expect some kind of symmetry axis here, and I do get that. So what you find, though, is up here in a region which is asymptoting towards this axis, so lambda equals 0, I have reverse Ostwald for bubbles. The case I've been talking about in these Austral calculations was always for a dense droplet, but you can obviously completely do everything again for a bubble surrounded by a dense liquid. And again here, so this is just basically the mirror image of that. Not the mirror image, but okay. Reverse Ostwald for droplets or clusters. In other words, in these regions, if I start with a bunch of droplets of various sizes, instead of the small ones shrinking and the large ones growing, which leads to bulk phase separation, the small one, they do the fair thing, as any school child would tell you, which is that they all converge to the same size. Small ones grow, big ones shrink. That's microphase separation. That says I've got droplets which are all the same size, and so I have a length scale. So in the region, in that reverse Ostwald region, so RO reverse Ostwald, mean field says droplets converge to the same size, but there's something awkward about that. If you think about it, if that's all that's happening, the size that you get is set by the average of the size that you started with. And so that size is selected by the initial conditions. So there's still something a bit wrong with this calculation. And in practice, when you look at what happens in the microphase separated regimes, which do roughly correspond in parameter space to these, in practice, so in other words, not in mean field theory, with noise, the mean size is noise dependent, which is was an answer to a question Julian asked earlier. So we don't understand the relation between the noise and the mean size. Yes.
Do you have an instability for large droplets?
No. So you might say I've got a negative. So you might say I've got a negative tension. So why don't I have an unstable interface? And again, it's a little bit like the active model H calculation. This is a negative surface tension for the purposes of Ostwald ripening in a spherical geometry. That does not mean that the interface is locally unstable towards capillary ripples, because that's a different surface tension, or rather the whole premise of this is that that's an effective surface tension which involves doing this non-local thing. And there's nothing actually about the non-local thing which makes the interface itself unstable. What it does do is it makes the relation between the densities inside and outside such that you've reversed the relation between that and R. So it's the many body droplet system which is changed in behavior, but not a single droplet on its own. So that's a good and important point. Okay. Yes. Yeah. So if you start with droplets of various sizes, and the big ones shrink and the small ones grow, then they will have to, in a stationary state, they have to all be the same size. I mean, that's the only fixed point of that dynamics. But the point I was making is that size depends on what you had initially as your sizes. In other words, in particular, if I prepare a system with nearly the same size for the droplets, I could use any size for that, and it would just gently settle towards the mean, and then that will be separately metastable. So there has to be, in a system where you do a quench or you have noise, there has to be something which selects the droplet size other than that. So the noise seems to do it, but we actually don't know the mechanism of that. So mechanism unknown. So again, for further discussion of that, you might want to see the Chung et al. Archive paper. This year. And on that note of complete ignorance, I think that would be a good place to stop. So thank you for your attention. Bon. I feel exhausted. You must feel completely knackered.